Okay, now I'm going to do deflection, the final lecture that you need for your project. And what I'm going to do is really just work through the example, or just run through the example with you, because the example is almost identical to what you need for your project. It's a parabolic pre-stress profile, and it's a UDL, so you'll use everything exactly the same as this example. You'll use that for your project. I just need to point out a few things. The self-weight of the beam is obviously going to induce a downward deflection just from the self-weight. The pre-stress is going to give you an upward deflection, also referred to as a camber. And quite often, after we've applied the pre-stress, we're left with an upward deflection of the beam until such time you start to apply your live load. Okay, so I'd like you to read through all of this, and in fact, in your textbooks, go through it as well, because I've basically extracted this directly out of your textbook. So go through it, and I just want you to follow the example in the textbook and follow the example here, and then try and run through your own example for your project. You need to look at a few things. At transfer, where the pre-stressing force is at its highest and the long-term losses haven't occurred yet, so we've got the least self-weight as well, because we haven't put the superimposed dead weight on. The result is that the delta P is greater than the delta W, with the resultant being an upward camber. So the pre-stress deflection upwards is going to be greater than the dead load deflection downwards, most likely. Okay, under service loads, after we've suffered long-term losses, and that the pre-stressing force is at its minimum, but the service loads are acting at its maximum, that's when we might have the pre-stress deflection leveling out a little. And then creep and shrinkage has a big play on that as well. Now let's just go through this example. Obviously I want you to work through this yourself, but I just want to go through the example. If I should maybe just explain this table 8.1 from Marshall and Roberts first. If you look at this, we're using a parabolic shaped pre-stress profile. Our E2 value that we're looking at there is obviously 0, because we're going to be coming in, we've been coming into the neutral axis. Okay, so when that's 0, the second half of the equation just falls away. And then of course over here, our UDL is going to use that, and this is a very familiar formula. You'll be familiar with that already. If we had a point load or a pair of point loads, you would have used these formulas further on down the line, but we're using that, and that's exactly what we've used in the example that we're going to go through. So this is very, very similar. Okay, so go through these notes yourself, but very, very similar, this example, to what we've got in our project. So the things you're going to need to do, you're going to need to know your effective pre-stress at mid-span. Of course, you know that. So you need, because you've already calculated your long-term losses, so you won't need to factor it. You will just use whatever your long-term loss is, what your pre-stress is after long-term loss, and you'll know that already. Okay, what we do need to do, the first step that we see here, is we need to estimate the modulus elasticity of the concrete at transfer, because as you know, when we transfer the pre-stress to the concrete, it's not fully mature at 28 days. So we have to follow this process. It's a straightforward formula. Just use the formula 2.5 as given. And we have to just remember that. We've got a transposed Young's modulus for the immature concrete, and we only use that in the early stages. We'll see now where we use it. And so that second formula I showed you on that table, I think it was table 8.1, was it? Yes, table 8.1, this formula. Okay, just follow this, guys, really straightforward. And then transfer deflection due to self-weight. Obviously, we've got the very minimal self-weight that we're going to be using. So in this example, you can see that your upward deflection due to pre-stress is almost 42 millimeters, and downwards from the self-weight is only 26 or so. So it leaves us a net upward deflection in this particular instance of 16 millimeters. I'm expecting something similar might happen with your project as well. Now when we get to the long-term deflection, you'll see, let's just go back here firstly to the short-term deflection here. We've used this E value, where we used the short-term E value, the one that we've just calculated. See the 25.1. This was for the immature concrete. Right, from now on, in the long-term deflection, we're going to start using the full E value. So we must remember that. Don't carry through that other value that we used earlier. The N that we're going to use here, this nether factor, don't use the one you estimated, use your actual long-term losses. Okay, don't forget that. Right, you need to calculate the perimeter of your structure. That's very straightforward. That's just easy maths. You need the area of your structure. You're going to get an effective section thickness over here. This will take you to the figure in 216. From that nomograph, depending on what your relative humidity is and so on, I don't know if I gave you the relative humidity. I think I said it was in Durban. So you're going to have to pick a suitable one of these lines. So whatever percentage you pick, transfer across to the closest of the sections that are closest to whatever your effective section thickness is, and you're going to get this phi mu value, this factor. You're going to get that. It should be round about the same as this example as well, actually. Okay, we need to calculate basically the slope of the deflection that's going to take place during creep and shrinkage. As to this first part is, just follow the formula, really simple. Keep following it through, and you're going to get a long-term upward camber, which is basically a factor of that 2,4 that we spoke about. Long-term deflection due to permanent loads, we've got a minimum and a maximum that we have to work to. This is basically the minimum will be just the self-weight, and the maximum will be the self-weight as well as, and see this example didn't have a superimposed dead load, but our project does, so you would have to add that here. And you're going to have to calculate this both the minimum and maximum deflections. Simple formula, keep following it. Just remember this E effective, just follow that as well. That takes into account the fact that we put the creep factor into the Young's modulus. Okay, and we'll calculate a downward creep from the minimum load, and a downward creep from the maximum load. Shrinkage deflection, once again, just follow page 889 of Marshall and Roberts. The B of the beam, I would suggest we use 900. Just neglect those little flange thingies on the edges. Okay, and we calculate from this nomograph, we calculate this epsilon SU factor that we need. Okay, and we carry that through to our other formula. Just keep following this, exactly the same. And of course, the final one, just deflection due to live load. This is exactly the same as any other normal elastic calculation. Right, carry these through, do a summary just like we've got here. The only thing that's different is this comparison that we're looking for our project. We wanted an actual deflection limit of span over 500, not span over 250. Remember, I gave you the reason for that. It's a monorail beam. We don't want the monorail to have to go through this up and down motion if it's got too much deflection. Okay. Before signing off, I just want to mention one thing. The other thing that I've had a lot of queries about, and again, I'm just going to draw the shape of this thing. It's got nothing to do with deflection, but I've just had the queries about this. If this was our typical beam shape, like that, in the ultimate limit state moment calculations, a lot of people were saying that the depth of compression is going beyond the flange depth over here. So the easy workaround there is to ignore the flanges, like that, as if they weren't there, and just use the core width of the beam to calculate your compression zone. And as long as that is above the neutral axis, you're safe and happy, and you can continue with your calculation. You can work out what your ultimate moment capacity of the beam is, and you can compare it with your actual ultimate moment capacity, and it should sail through nice and easily. Okay. If there's any other questions, you can always WhatsApp me, or you can email me, and I'll answer them. I'm going to post these now, and you guys can reference them. Okay, cheers.